For most of human history, we believed the universe was defined by what it contained. Stars burning through nuclear fire. Planets locked into precise orbits. Galaxies colliding, merging, and tearing each other apart across cosmic time. Even after astronomers accepted that space itself was mostly empty, that emptiness was treated as passive, a silent background where matter performed the real story. But modern cosmology is forcing us to confront a far more unsettling idea. Some of the strongest influences shaping the universe may come not from what exists, but from what doesn't. Across the largest observable scales, the universe is not smooth or evenly distributed. Galaxies do not appear randomly scattered. Instead, they form a colossal structure often described as a cosmic web. Long filaments of matter stretch across hundreds of millions of light-years. Massive galaxy clusters form where these filaments intersect. Dense walls of galaxies surround enormous regions where almost nothing exists. These regions dominate the universe by volume. They are known as cosmic voids. Despite the name, cosmic voids are not small gaps or rare anomalies. They make up most of the observable universe. Some voids are tens of millions of light-years across. Others span distances so vast that light needs hundreds of millions of years just to cross from one side to the other. For decades, astronomers assumed these regions were unimportant, simply places where matter failed to collect. But that assumption turned out to be dangerously incomplete. A cosmic void is not absolute nothingness. There is still dark matter. There is still dark energy. There are still faint traces of gas, radiation, and the occasional isolated galaxy. What is missing is concentrated mass. And that absence fundamentally changes how space behaves. Gravity depends on mass. Where mass is scarce, gravity weakens. And where gravity weakens, space expands with less resistance. In dense regions of the universe, gravity slows expansion. Galaxies pull on one another. Space stretches, but it does so reluctantly. Inside a void, that resistance almost disappears. Matter flows outward toward denser regions nearby, leaving void interiors increasingly empty. Over billions of years, voids grow larger and emptier. In a very real sense, they are the fastest expanding structures in the universe. This behavior leads directly to one of the most persistent problems in modern cosmology. The expansion rate of the universe, known as the Hubble constant, does not agree with itself. When scientists measure expansion using ancient radiation left over from the early universe, they obtain one value. When they measure expansion using nearby galaxies and exploding stars, they obtain another. These two methods should converge. They do not. The discrepancy is small in absolute terms, but enormous in its implications. Every improvement in precision has made the disagreement sharper rather than smaller. This tension suggests that the universe is not simply hiding a measurement error. Something deeper is missing from the picture. One possible explanation is both simple and deeply uncomfortable. What if part of the discrepancy arises from where we are observing the universe from? If Earth happens to lie near a large cosmic void, the local expansion of space around us could be slightly faster than the cosmic average. Nearby galaxies would appear to be receding more rapidly, not because the universe is expanding faster everywhere, but because we are measuring expansion from inside an underdense region. This idea does not require exotic new physics. It does not violate known laws. It relies only on the large-scale structure of the universe itself. Light traveling through space does not move through a uniform environment. As it journeys across billions of light-years, it passes through regions of different gravitational strength. In dense regions, gravity drains energy from light, subtly altering its wavelength. Inside a void, gravity is weaker. Light loses less energy as it travels. Over hundreds of millions of light-years, these small effects accumulate. Brightness measurements shift. Redshifts change slightly. Distances inferred from light become subtly distorted. Each effect is tiny on its own. But cosmology depends on patterns repeated across enormous scales. Small distortions, applied consistently, can reshape conclusions about how fast the universe is expanding and how its history unfolded. Even time itself behaves differently inside cosmic voids. According to general relativity, gravity affects the flow of time. In stronger gravitational fields, time slows down. In weaker gravity, time speeds up by a tiny amount. Inside cosmic voids, where gravity is weaker than average, clocks tick slightly faster than they do in dense regions. This difference is far too small for humans to notice, but over billions of years, it accumulates. Void regions experience subtly altered cosmic histories. Expansion proceeds differently. Structures evolve at slightly different rates. The universe is not perfectly synchronized. Dark energy remains the leading explanation for the accelerating expansion of the universe. But cosmic voids complicate how that acceleration is measured and interpreted. Voids do not replace dark energy, and they do not make it disappear. But they may amplify its apparent effects. Some of the acceleration attributed to dark energy could be enhanced by large-scale emptiness itself. That does not make dark energy an illusion. It makes the universe far harder to read than we once believed. Modern cosmology relies on a foundational assumption known as the cosmological principle, the idea that the universe looks roughly the same from any location when viewed on sufficiently large scales. Cosmic voids do not destroy this principle, but they place it under pressure. If observers in different regions experience slightly different expansion histories due to large-scale structure, then perspective matters physically, not philosophically. The universe may be statistically uniform, but locally biased. Today, astronomers are doing something unprecedented. They are mapping emptiness. By tracking the motion of millions of galaxies, scientists can outline the shapes of cosmic voids with extraordinary precision. They study subtle distortions in galaxy velocities, gravitational lensing patterns, and faint imprints in ancient radiation. The goal is not to discover what voids contain, but to understand how voids influence everything else around them. Cosmic voids affect galaxy formation, gravitational lensing, expansion measurements, and even the interpretation of the oldest light in the universe. They are not background noise. They are part of the signal. Ignoring them would be like studying climate while pretending air pressure does not exist. For centuries, humanity searched the universe for substance. Then we discovered that most of it was invisible. Now we are facing something even stranger. The universe may be shaped not only by what fills space, but by what empties it. Cosmic voids do not shine. They do not explode. They do not announce themselves. Yet they quietly define the largest patterns in existence. The most powerful influence in the cosmos may not be matter or energy, but absence. And the deepest mysteries of the universe may not be hidden inside stars, but in the vast, silent spaces between them.